Welcome to our Bioprocess Engineering online tutorial on LCA Guided Bioprocess Environmental Optimization. Through the Bioprocess Engineering online tutorial series, you gain expertise in the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, please visit us at bioprocessengineeringonline.com. In this introductory tutorial on the environmental optimization of bioprocesses, we'll address three questions. Which environmental optimization criteria of bioprocesses? How to reduce the environmental impacts of bioprocesses? And, as an example, how to optimize the glutamate fermentation bioprocess. The primary aim of bioprocess engineering is to enhance the efficiency and effectiveness of bioprocesses, encompassing both their design and operation. This entails optimizing the entirety of bioprocessing, including upstream and downstream unit operations. Foremost among these optimization goals is economic efficiency, with a focus on reducing production costs per unit of product, typically measured in either euros or dollars per kilogram. Concurrently, there is a growing imperative for environmental bioprocess optimization. This entails evaluating and minimizing the environmental footprint of processes through indicators derived from comprehensive life cycle assessments, LCAs. Environmental optimization targets the reduction of impact indicators per unit quantity of product. In life cycle assessment, impact indicators serve as measurable variables that assess the contributions of material and energy inputs and outputs throughout a product's life cycle. These indicators account for the environmental contributions of emissions and waste generated during the process, as well as of the utilization of material and energy resources across various stages of production and transportation. Each impact indicator, denoted as IMP, is derived by aggregating the impact contributions of all inputs and outputs. This calculation is formulated as follows. IMP equals sum of MI multiplied by FI, where MI represents the quantities of inputs and outputs from material and energy inventories, and FI denotes the corresponding impact factors per unit quantity of input or output. For bioprocesses, there are typically three major LCA environmental impacts to consider. Firstly, primary energy consumption PEC in megajoules. Bioprocesses often exhibit high energy consumption, particularly for the operation of fermentation and thermal unit operations, such as sterilization, evaporation, and drying. Secondly, water consumption watt in kilograms water. Bioprocesses can entail significant water usage for media and buffer preparations, as well as equipment cleaning. Thirdly, global warming potential GWP in kilograms of CO2. In bioprocesses, there are notable levels of CO2 emissions during the fermentation stage and from energy consumptions. Bioprocesses exhibit a broad spectrum of impact indicator values influenced by factors such as the enzymatic, microbial, or cellular transformations involved, the nature and extent of upstream and downstream operations, and the purity standards required for the final product. For instance, primary energy consumption, IPEC typically ranges from 10 to 10,000 megajoules per kilogram. Water consumption, IWatt, ranges from 1 to 10,000 kilograms of water per kilogram of product. Global warming potential, IGWP, varies from 1 to 1,000 kilograms of CO2 per kilogram of product. Generally, bioprocesses indicators tend to fall within the lower end of these ranges. However, certain products, such as therapeutic proteins, demand rigorous purification via chromatographic steps. These steps necessitate substantial quantities of buffers and purified water, resulting in very high impact indicator values. In order to develop an environmentally optimized strategy for bioprocesses, it is imperative to comprehend the factors affecting their three major environmental impacts. These impact indicators are typically influenced by several key factors, including 1. Bioprocess flow sheet and unit operations. The arrangement and sequence of unit operations involved in converting raw materials into the final product significantly impact environmental outcomes. This includes considerations of equipment efficiency and design. 2. Raw materials and chemicals. The choice and sourcing of raw materials and chemical reactants play a crucial role in determining environmental impacts. Additionally, the amount and quality of water used in the process contribute to overall environmental performance. 3. Energy sources. The selection and utilization of energy sources, such as electricity, gas, or fuel, have a direct bearing on environmental sustainability. Opting for renewable or low-emission energy sources can mitigate environmental burdens. 4th, operational conditions. The operational parameters of the bioprocess, including batch, continuous, or fed batch modes, as well as variables like concentrations, flow rates, and temperature, influence environmental impacts. Fine-tuning these parameters can lead to efficiency gains and reduced environmental footprints. By comprehensively considering and optimizing these factors, bioprocesses can be tailored to minimize their environmental impacts while maximizing efficiency and product quality. The strategy for environmental optimization relies on a thorough analysis of the life cycle assessment of the bioprocess, particularly focusing on the relative impacts of various material and energy inputs and outputs. This analysis identifies the key contributors that influence environmental performance. In bioprocesses, significant factors affecting indicators such as primary energy consumption, water consumption, and global warming potential typically encompass raw materials utilized in biotransformation, water consumption, CO2 emissions from fermentations, as well as electricity and gas consumption. Clearly, the environmental optimization strategy should prioritize reducing the impact of these major contributors. The environmental optimization strategy is further informed by a sensitivity analysis of impact indicators relative to various process variables. These variables encompass the kinetic parameters of enzymatic or cellular biocatalysts, as well as operational factors such as concentrations, temperature, flow rates, and operation duration within unit operations. The sensitivity coefficient, denoted as SI, XI, quantifies the impact indicator's responsiveness to changes in a specific process variable, XI. This coefficient is determined through the use of a bioprocess LCA simulator, where it is computed as the relative variation in impact indicator, resulting from a relative variation in the input variable. By evaluating the sensitivity coefficients, one can prioritize which process variables to address in order to notably diminish the impact indicators. By pinpointing environmentally critical inputs and outputs, life cycle assessment offers invaluable insights for optimizing bioprocesses environmentally. Several strategies for reducing the impact indicators of bioprocesses include enhancing biotransformation efficiency to elevate final product concentration, bioreactor productivity, and substrate conversion yield, improving biocatalysts to boost biotransformation efficiency, implementing water recycling within or between operations, incorporating heat recycling within or between operations. Glutamic acid, or glutamate in its ionic form, is industrially produced through a fermentation process, utilizing selected strains of Corynebacterium glutamicum. Within bacteria, the excretion of glutamate can be triggered, for instance, by elevating the temperature of the medium. The production process of glutamate encompasses upstream operations such as media preparation, sterilization, and fermentation. Downstream operations involve centrifugation of the cellular biomass, concentration of the glutamate solution through evaporation, crystallization of glutamate, and final drying to obtain dry glutamate crystals. The residual crystallization liquor is concentrated through evaporation and valorized as animal feed or fertilizer. The material and energy inventories of the glutamate bioprocess are established based on a production plant equipped with a 200 cubic meter fermenter. Under non-optimized conditions, each batch typically yields approximately 14,000 kilograms of glutamate. For every kilogram of glutamate produced, the process requires 2.2 kilograms of glucose, zero point 0.2 kilograms of ammonia, zero point 0.1 kilograms of salts and minerals, and 19 kilograms of water. At the same time, zero point 0.7 kilograms of CO2 and zero point 0.8 kilograms of vinasses are generated. In terms of equipment operation, the process consumes 1.2 kilowatt-hours of electricity and 1.5 cubic meters of gas per kilogram of glutamate produced. Under non-optimized conditions per kilogram of produced glutamate, the impacts indicators are as follows: 130 megajoules for the primary energy consumption. The two most important contributions are from gas and glucose. 40 kilograms water for the water consumption. Main contributions are from fermentation media water and glucose. 7.5 kilograms CO2 for global warming potential. Most important contributions are from gas and glucose. Accordingly, for the three impacts indicators, it is the production of the glucose used in the fermentation medium, the water for media preparation, and the gas for fluids heating that bring a dominant contribution to the glutamate process environmental footprint. The environmental optimization strategy for the glutamate process is more precisely defined through a sensitivity analysis of impact indicators concerning various process variables. Sensitivity coefficients, denoted as SI, XI, quantify the relative changes in impact indicators resulting from variations in input variables. According to this analysis, for the 3 PEC watt and GWP indicators, the variables most influential are primarily those pertaining to bacterial kinetics. Specifically, the glucose to glutamate and glucose to biomass stoichiometric coefficients, along with the cell's glutamate excretion capacity, exhibit the highest sensitivity. The second set of influential variables encompasses those associated with fermentation operations, notably the initial glucose concentration and the thermal induction time for glutamate excretion. The first approach to reduce environmental impacts of the glutamate production process is the optimization, the central fermentation step. For the batch glutamate fermentation, this is achieved by adjusting the initial sugar concentration and the time of thermal induction to reach the highest fermentor productivity. The optimization of the two operational variables results in an increased glutamate production from 14,000 to 18,000 kilograms per batch. This fermentation optimization results in a decrease of the 3 PEC watt and GWP indicators. The second approach to reduce environmental impacts of the glutamate production process is the improvement of the Corynebacterium microbial strain. The selection of a strain with a higher glucose conversion yield into glutamate and a higher glutamate excretion rate results in an increased glutamate production from 18,000 to 21,000 kilograms per batch. This strain improvement results in a further decrease of the 3 PEC watt and GWP impacts indicators. In the glutamate production process, water is used for the preparation of fermentation media. Simultaneously, water is generated during 2 evaporation stages, which concentrate the clarified glutamate solution in crystallization liquor into vinasses. The implemented water recycling strategy consists in using the evaporated water for the preparation of the fermentation media. This results in a significant decrease of the water consumption indicator. The production process of glutamic acid demands significant quantities of heat for sterilization, evaporation, and drying operations. These operations rely on the condensation of steam and the combustion of natural gas to provide the necessary heat. Efforts to reduce heat and gas consumption involve the recovery and recycling of heat within and between operations. For example, continuous media sterilization can benefit from preheating the incoming cold medium using a heat exchanger with the outgoing hot medium. Multiple effects evaporators utilize the steam generated in one evaporator to heat and evaporate water in subsequent stages, minimizing energy input. Additionally, heat recovered from the hot fluids produced in evaporators can be utilized to warm the air for the glutamate crystals drying process. By implementing these heat recycling techniques, there is a significant reduction in the primary energy consumption indicator. In conclusion of this case study, examining environmental optimization of the glutamic acid production process, the implementation of 4 key strategies: process optimization, strain improvement, water and heat recycling, stands out as highly effective in reducing the process's environmental footprint. When employed together, these strategies can achieve a remarkable reduction of up to half in the 3 impact indicators of primary energy consumption, water consumption, and global warming potential. In summary, in this introductory tutorial on bioprocesses environmental optimization, you learned utilizing process lifecycle assessment as a tool to guide the environmental optimization of bioprocesses, implementing strategies to reduce the environmental footprint of fermentation bioprocesses. They include optimizing the fermentation operation, enhancing microbial strains, and incorporating water and heat recycling procedures. If interested, you can gain a deeper insight in the LCA methodology by enrolling to one of our online courses: Introduction to Bioprocess Lifecycle Assessment and Lifecycle Assessment of Bioprocesses and Bioproducts. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.